Hello, everyone. So this is the second day of the IBS conference on flat bands. And I'm Alexey Andrianov. I will be the chairperson for today's session. So our first speaker is Jun-Won Rhim from our university, and he's going to talk about novel geometric aspects in flat band systems. So Jun-Won, please, you have your 30 minutes.
Yes, thank you. And good afternoon or good morning, everyone. And first, I would like to thank the organizers for inviting me to this fantastic conference. And as introduced, I'm Jun-Won Rhim. And today I'm going to talk about some interesting geometric aspects in flat band systems. Before starting my talk, I want to introduce my collaborators. So this is Professor Bom Jung-yang at Seoul National University, who is also one of the organizers of this conference. And this is Yoon-Seok Hwang. He's a student of Bom Jung-yang, and he did many flat band works with me and Bom Jung-yang, like Superman. And this is Dr. Gyu Kim from Korea Atomic Energy Research Institute, who did the DFT calculations and DFT plus U calculations for us. And this is Dr. Daniel Lay Kem from National University of Singapore, who did the theoretical analysis with us for the photonic crystal experiments. And in the second row, I have an experimentalist from Nankai University. They did very nice photonic lattice experiments from the flat band systems. This is Professor Jigang Chen and Lin King Tang, and these are members of their group in the Nankai University. Okay, so today I would like to start by mentioning that the major part of the modern solid state physics is in the era of Berry, and two key geometric notions in this era are Berry connection and Berry curvature, as defined here. So Berry connection is an inner product between a quantum state denoted by NR and its derivative with respect to certain parameter R. This parameter would be crystal momentum in the solid state systems. And the core of this Berry connection is called Berry curvature. So the Berry curvature actually appears as an effective magnetic field in the semi-classical description of electron wave packet in a solid, while this first term is nothing but the group velocity, which can be obtained from just seeing the band structure. The second term is important, which is proportional to the Berry curvature and gives us many anomalous behavior in solids. Okay, for example, quantum Hall effect or anomalous Hall effect and Belly Hall effect and so on, especially in this transfer phenomena, many intriguing phenomena arising from this second term proportional to Berry curvature. And actually, if we look at this quantum Hall effect, the quantum Hall conductivity, this is proportional to an integral of Berry curvature over the whole Brillouin zone. And this integration is called the Chern number, which is an integer number. And this is actually so-called topological invariant and has been the key player for the topological analysis of solid state systems. So in this way, Berry curvature played a very crucial role in the modern solid state physics. And another geometric quantity is the Berry connection. This was used in defining electric polarization, so-called the modern definition of electric polarization by Vanderbilt and King-Smith. And they found out that the Z phase in the red box, which is obtained by integrating Berry connection along one direction in the Brillouin zone. And they found out that by using this Z phase, we finally have a correct definition of electric polarization, which does not depend on the choice of unicell actually. So this is a very nice quantum definition of electric polarization. And by using this electric polarization, we can have some information about the edge profile, because polarization is closely related to this edge charge accumulation. By using this, actually, we can determine whether there is in-gap edge states or not when there is a certain symmetries like reflection symmetry. And in such one-dimensional systems, we can have so-called one-dimensional bulk boundary correspondence by using the Z phase. Okay, so in this way, Berry connection and Berry curvature has been very key notions in modern solid-state physics. Okay, but how about other notions in geometry like distance or metric? So actually, there are also a very long time ago already, they defined distance and metric notion in this quantum mechanical wave functions, so-called quantum distance, or full name is the Hilbert-Schmidt quantum distance, which is defined as like this red box, which is square of quantum distance is equal to 1 minus overlap between two quantum states, Vk and Vk prime square. So this definition tells us how the states are close or far from each other. When Vk and Vk prime are identical to each other within U1 gauge, then they are said to be distance equal to 0. But when those two states are orthogonal to each other, this overlap becomes 0, and the distance becomes 1, which is the largest distance possible in the quantum distance definition. And this kind of quantum distance concept was first introduced, as far as I know, by Provost and Bali in this mathematical physics journal, and also reviewed by Michael Berry in his another paper after his original seminal paper on the Berry curvature. Okay, but okay, so and this quantum distance, when we make close this k and k prime to each other, then we can have this infinitesimal distance between two quantum states. And if we expand, we have this kind of formula in the second row, which proportional to dki and dkj. And this coefficient is actually, naturally, we can define this coefficient as a quantum metric. This is kind of a metric in geometry. So by using this definition of a Hilbert-Schmidt quantum distance, naturally, we have a quantum metric in this way. And actually, there have been several works related to this quantum metric. For example, the first one is the experimental paper to measure the quantum metric in some optical system, planar microcavity. And the other ones are theoretical works related to quantum metric and their physical implications in superfluid weight and current to noise and orbital magnetic susceptibility. In these physical quantities, this quantum metric plays some crucial roles actually. But these studies on the quantum metric compared to Berry curvature and Berry connection, this business is quite small yet. And I think there can be many things to be discovered about this quantum metric or quantum distance. And in this talk, maybe one of the conclusions might be flat bands are an ideal platform for studying the quantum metric and quantum distance. Okay, so I think in this conference, everyone knows what is flat band systems. So I briefly just introduce you what is flat band. So flat band is a dispersionless band, like a Kaguman lattice with only nearest neighbor hopping. We have a flat band at the bottom. And this flat band has group velocity 0 and effective mass infinite. Due to this property, interactions between electrons becomes extremely important, and people expect many body ground states can be induced very easily in the flat band systems. And this is why there have been constant curiosity and interest in these flat band systems. For example, ferromagnetism by Hart Tasaki, and flat band superconductivity by Bolovig and Heikila, and the Vigano crystal in flat band also studied. And most importantly, very recently, people experimentally synthesized twisted bilayer graphene at magic angle with a flat band, and they really found out some intriguing superconducting phases are there when the flat band appears. So this discovery actually boosted the study on the flat band systems recently. But our concern is actually a little far from this many-body physics. Our concern is about non-interactive physics, actually, and the Bloch, some intriguing properties of a Bloch wave functions of a flat band case. And this is quite counterintuitive because previously, in many cases, flat bands are considered topologically trivial because of this mathematical physics study. They rigorously proved that if we consider finite hopping systems, such type binding Hamiltonian, if such type binding Hamiltonian have a flat band, the flat band always have a finite Chern number, zero Chern number. So in topological sense, the flat band is trivial. This is because such flat band, exact flat band, cannot have any singularity in the Bloch wave function. The only way to have a singularity in the Bloch wave function in flat band is to have a band crossing with another band, as shown in the right-hand side. Okay, in this case, the Bloch wave function have a certain singularity. I will explain soon. But even in this band crossing case, if we calculate Berry phase around this crossing point, it always trivial, like a 2 pi n. Okay, so even if it has a singular property in conventional topological sense, it is not that much interesting. So, but the good thing might be that because these topological properties are suppressed in the flat band systems, the other geometric quantities, such as quantum distance or quantum metric, could be crucial. Okay, so this is a major motivation to study some geometric aspects in flat band systems. And this singularity in flat band is actually defined like this. We look closely the wave function of the flat band, and we unnormalize this eigenvector of the flat band in this way without any common factor between vector components and only finite sum of Bloch phases at each component of the eigenvector of a flat band. If we make such unnormalized eigenvector of the flat band, this singularity appear as a simultaneous zero of all the components of the eigenvector. So at this singular point, the eigenvector of the flat band becomes exactly zero. Then this is set, this is we call singular flatband. Okay. This singular flatband, we found very interesting properties. First, if there is such a singularity, we found out certain topological loop states are guaranteed, which is called the non-contractible loop state. So, for example, in Kagome lattice, this Kagome lattice has a singular band crossing, and due to this singularity, we can have this kind of eigenstates. These numbers are amplitude of this eigenstate, and this is extended along certain direction, but compactly localized the other direction. If we put these topological non-contractible loop states on the periodic boundary condition torus geometry, they actually rounding this torus along poloidal and toroidal directions. And actually, this is non-contractible because we cannot cut these loop states by just adding compact localized eigenmode of the Kagome lattice. So it cannot be cut and very robust. And because it cannot be cut, we cannot make it a certain localized mode from this extended mode. So this is why we call this is topological states, and this is guaranteed by singularity of the wave function. And if we make open boundary from this periodic boundary condition, we can cut the periodic system in this way, and we prepare 4 non-contractible loop states like this, and we cut between them, and we realize this open boundary system, and these 4 non-contractible loop states becomes a boundary mode surrounding the boundary of this finite system. For example, in Kagome lattice, we can find these eigenstates surrounding this boundary of Kagome lattice, and this is also very robust in the same risk with the same risk of this with this previous periodic system. We cannot cut this rounding states. We just deform actually by adding compact localized states. In that sense, this is robust. So this is a kind of a new bulk boundary correspondence existing in flatband system due to the singularity of the flatband eigenfunction. And we actually experimentally realized this robust boundary mode in the photonic lattice by collaborating with Zigang Chen's group. And we realized Kagome lattice here and realized the robust boundary mode. And by adding compact localized states, we cannot cut this line mode. We just deform in this way. Okay. And the next thing is about some more physical properties of this singular flatband related to the quantum distance. And we actually, to study that, we concentrated on more simple system. It's a two-body Hamiltonian with a flat band and quadratic band touching. And in this case, the singularity becomes a discontinuity of the flat band wave function. So the normalized eigenvector becomes discontinuous in this simple 2x2 Hamiltonian at the touching point. And this is described by this very generic 2x2 Hamiltonian. This is Pauli matrix, sigma x, sigma y, and sigma z. And fx, y, z are quadratic functions of crystal momentum. And you note there are very many parameters, system parameters, 9 system parameters from B1 to 3 and T1 to 3, 4, 5, 6. But due to the flat band condition, we only have 4 independent parameters in this case. And if there is a singularity at the touching point, actually we found out that the quantum distance have a following property. Actually, we can measure the distance, quantum distance between any pair of states, quantum states around this touching point. on this very small circle. And we can measure the distance between them, and we pick up the maximum value among them. And this is called the Dmax. And in the singular flatband case, the Dmax is non-zero. Okay, this is the very characteristic property of this singular flatband. And this we propose that the discontinuous singular flatband of this type is characterized by non-zero Dmax. Okay, if there is no singularity, the maximum distance becomes zero, because all the states around this touching point can be continuously connected without singularity. But when there is a singularity, Dmax becomes finite. And Dmax actually represents the strength of the singularity. This is also our purpose. And this Dmax quantifies strength of actually the interband coupling between flat band and quadratic band touching with it. And another something we can visualize about this Dmax is that because we have a 2x2 Hamiltonian, we can naturally define pseudospin around this touching point. If we draw this pseudospin structure around this touching point, actually they have a canting structure when there is a singularity. If Dmax is finite, we have such a canting structure, even if we get to very close to the touching point. But if Dmax is zero, these pseudospin align to each other. So this is a very interesting extreme opposite of graphene actually. In graphene, we have a zero effective mass and pi Bethe phase. But in our singular flatband, we have an infinite mass and we have a finite Dmax. Okay. Then how to measure Dmax? So we found out that Landau level spreading is a very nice physical phenomena manifesting this finite Dmax actually. So we still stick to this continuum Hamiltonian, 2x2 Hamiltonian, and we assume flat band is at the zero energy, and we simply apply the magnetic field perpendicular to the system and see what happens to the Landau level. So if the Dmax is zero, which is the case of a non-singular flat band, the Landau levels of the flat band shows nothing. They stay at the zero energy even after the Landau magnetic field is applied. But in the case of a singular flat band, that is Dmax is finite, then the Landau levels are developed below the flat band in the gap region. Okay, we call this as the Landau level spreading. We thought that this is quite interesting because according to the conventional semi-classical idea by Onsager's semi-classical theory, we only have Landau levels within the energy region where band is existing. In the gap region, usually we don't expect actually Landau levels, but in this singular flat band, we have a certain spreading into the gap of this Landau level. And we denote this Landau level spreading as delta. And we have a plot between the ratio of delta and the h-bar, the cyclotron energy of this quadratic band shows a very universal curve with respect to Dmax actually, this quantum distance, maximum value of the quantum distance. And these diamond markers symbols are the value of this ratio for any arbitrary parameters of this 2x2 Hamiltonian. Even if we put any kind of arbitrary parameters for this calculation, we actually find out this ratio is solely determined by Dmax. This was we found very interesting, and this tells us that Dmax is manifested in this Landau level spreading. Okay, and okay, this was quite contradicting to the conventional semi-classical idea, and we also examined concrete lattice models like Kagome lattice, because before we only consider the continuum Hamiltonian, we want to know there is some corresponding lattice models, and we found out Kagome lattice satisfies this relation very well between Dmax and the Landau level spreading. You see there is a Landau level spreading, and it satisfies our major equation from the Dmax. And one interesting fact is that actually those Landau levels are proportional to 1/n, where n is the Landau level index. And also in Chekhov lattice, we found out our theory works very well. And we also calculated magnetic orbital susceptibility of such a singular flat band. And because of this 1/n dependence of these Landau levels, and the susceptibility is a second derivative of total energy below the Fermi level, we have actually harmonic sum, which is diverging. So we found out the orbital magnetic susceptibility becomes very high for the flat band, singular flat band. It's actually diverging, okay? And we also found out some realistic systems to realize this singular flat band by examining some network models of carbon atoms, so-called cyclic graphene, cyclic graphene, and cyclic graphene. By using DFT calculations, we were able to see there is a very flat band at the Fermi level, okay? And in these systems, we might be able to see the Landau level spreading and its relation to Dmax, actually. Okay, so this was one thing we found about the geometric aspects in the singular flat band systems. And we also curious about multiband generalization of our work. And we consider as a first step an isolated flat band. Actually, this anomalous Landau levels in the energy gap has been anomalous because of the Onsager's relation. We only expect Landau levels within the band before applying magnetic field. But from this work by Andrei Bonevik, they found out if if a band has certain topological aspects, like a fragile topology in this twisted bilayer graphene at the magic angle, they found out that such topological property can lead to in-gap generation of Landau levels. Okay, so it seems like that some topological aspects could be important in for having certain in-gap generation of Landau levels. But what we have found is that very general relationship is that even though we don't have any topological non-triviality of the flat band, we can have in-gap Landau levels from another geometric quantity, so-called the cross-gap barrier connection. Okay, so this equation is our major result, which can be applied to any kind of multi-band system for isolated single flat band. And the E and B is the Landau level. This is the modified band structure under the magnetic field of the flat band. And pi is the magnetic flux. And EM is the energy of other dispersible band from the flat band. And chi is actually the quantity, so-called fidelity tensor, obtained from this cross-gap barrier connection. Okay, so basically this represents how the flat band is deformed like this under the magnetic field. And this deformation is affected by other bands by interband coupling, and this is proportional to the energy difference from the other band and the flat band multiplied by this fidelity tensor. Okay, and we found out that this relation works very well. For example, before showing you the examples.
Jun-Won?
Yes.
Sorry, you have probably 2 or 3 more minutes, and then.
Okay, I'm almost there. Okay, thank you.
Good.
Okay, so before I defined quantum metric from the quantum distance by making these two states very close to each other. And in the same way, this is the fidelity. And if we make close this K and K prime again, we obtain this chi NM, the fidelity tensor, which was appearing in this formula as a multiplication between two cross-Gap-Barry connection. So this fidelity tensor is actually some kind of a very artificial metric when we define the fidelity as a certain distance concept. Okay. Anyway, this fidelity tensor we defined is another interesting manifestation of this geometric quantity cross-Gap-Barry connection, and this is reflected in the Landau level spreading of isolated flat band. Okay, and we tested many tight binding models, for example, Lieb lattice with spin-orbit coupling, and we found out that this flat band at the zero energy under the magnetic field, we have Landau levels as shown by these black lines, and their lower and upper boundaries are well described by our formula from the cross-Gap-Barry connection. And we also found out that certain symmetries can restrict this Landau level spreading. For example, if a system has a chiral symmetry, we always have no Landau level spreading. And if the system has a space-time inversion symmetry, we found out that the Landau level spreading starts from this quadratic dependence. The leading term is quadratic in magnetic field. The linear term dies in this space-time inversion symmetry cases. Okay, so this is a conclusion. So again, flat band systems are ideal platform to study various geometric properties of a Bloch wave function irrelevant to topology, and band crossing of a flat band where the Bloch eigenvector is discontinuous is characterized by Dmax, which is quite a big contrast to graphene's case. And also this Dmax of singular flat band is manifested in the anomalous Landau level spreading. And we also found out in the case of a very general isolated flat band can also have some geometric aspect related to cross-Gap-Barry connection. Okay, so this is it, and thank you for listening.
Okay, yeah, thank you, Jun-Won, for the nice talk. So now we have time for questions. We have time for a few questions. Okay, I do not see any yet, so let me start. I have a very simple question. So when you were mentioning the singular flat bands, do I understand it correctly, because that's something that always confused me, a sufficient and necessary and sufficient condition for the flat band to be singular is that if you look at the normalized eigenvector in the Bloch space, it turns 0 at some point. It's for some wave vector k.
Right, exactly. Yeah. I think there are several
right. Okay. Yeah, now I see it. So, Taro, please unmute yourself.
Thanks. This was a very interesting talk. I'm actually I try to understand this concept of the Dmax because from the point of view of the type of flat banks that I have been considering, did I understand it correctly that Dmax, yeah, it sort of describes the singularity, but then you say that if there is some chiral symmetry, the property related with Dmax is zero. So does this also mean that the Dmax is zero if you have chiral symmetry? So does it?
No, actually,
separate.
This Dmax actually about this chiral symmetry was related to isolate the flat band. I talked later part, but Dmax is about this kind of a system where flat band has touching with the quadratic band.
But and it all works with quadratic band. What if you have two sort of asymptotic flat bands touching? This is what happens, for example, in rhombohedral graphite in edge states.
Yeah, you mean when the quadratic band becomes flat?
For example. I mean, you can have asymptotically flat bands which are then touching. I mean, in rhombohedral graphite, it's actually not quadratic, but what you have is that you have two flat bands which have basically k to the nth. If you have a finite rhombohedral graphite, you have k to the nth dispersion where n is large, and this becomes asymptotically flat. And I'm wondering if this quantity is something that should be considered for that case.
Yeah, I guess so. I think, yeah, you may be right, but I didn't check explicitly yet. But okay. Yeah, I guess so. Yeah.
I will discuss this model in my talk, so maybe if you can discuss.
Yeah,
it.
Yeah, sure. Okay.
Thanks.
Thank you.
Okay, so then Christian, please unmute yourself.
Yeah, thanks for the extremely interesting talk. I have a simple question regarding the non-contractible loop states you showed in the first part, which you meant, yeah, exactly, which you mentioned are robust. Do you mean to say they're robust against imperfections of the boundaries? If you have a disordered boundary, will they still persist? Are they topologically, so to say, protected?
Yeah. So even if there is a local disorder,
yes,
it will be stable, just deform around this disorder.
Because you show this picture, the next slide.
Yes, this one?
So no, the previous one. So suppose those plus and minus ones have to reside on sides which support them, right? So if you just take one side away, would it still persist, you're saying? So it's...
Yeah, one side away, then it will connect it like this way. Can you see my...
Okay, then I get it, yeah. Right, yeah, thanks very much.
Thank you.
Okay, Dario, please unmute yourself.
Yeah, I mean, simple question about the end. I mean, do you understand the relationship between, let's say, which symmetry is present and why the Landau levels have certain features and not others?
You mean in the isolated flat band case?
Yeah, for example, you said when there is chiral symmetry, for example, the Landau levels do not appear and so on. Do you understand why?
Mathematically, it is very clear. And in this case, there is an odd number of bands. So if there is a chiral symmetry, we found out even if we apply magnetic field, this symmetry is still there. And this center band cannot be spread. Otherwise, the chiral symmetry is broken. But if there is an even number of bands, it can be spread. Yeah.
I see. Okay. I see.
In the case of space-time invergent symmetry, we think in this case, orbital magnetic moment can be zero, would be zero. And actually, our derivation of this modified band is from the orbital magnetic moment times magnetic field. So in that case, with the spatial time inversion symmetry, this linear term can be suppressed.
I see. Okay, good.
Thank you.
Okay, so yeah, with this, unfortunately, we don't have any time for further questions. So whoever is interested can ask questions to Jun-Won during the break. So thank you, Jun-Won. And
thank you.